Have you ever looked up at the night sky and wondered where it all began? Every star, every galaxy, and even the very space between them holds a story billions of years in the making. A story that starts with the most explosive birth imaginable. For decades, scientists have been piecing together the clues left behind by the Big Bang, and what they've uncovered is nothing short of breathtaking. We now know that in the first fraction of a second after the universe burst into existence, it underwent a period of unimaginable expansion called cosmic inflation, stretching far faster than the speed of light and laying down the blueprint for everything we see today. What's even more remarkable is how much our understanding has evolved in just the last few decades. We've moved from speculation to solid evidence, thanks to cutting-edge telescopes, satellites, and the brilliant minds daring to ask the biggest questions. These discoveries haven't just changed textbooks, they've reshaped our very notion of reality, hinting at parallel universes, hidden dimensions, and a cosmic recipe written in the faint afterglow of creation itself. In this video, we're going to explore 25 incredible revelations about the Big Bang and cosmic inflation that will completely redefine how you see the cosmos. From the first tiny ripples in spacetime to the vast web of galaxies we observe today, each discovery is a piece of the puzzle, bringing us closer to understanding our true place in this grand, expanding universe. So settle in and open your mind. We're about to embark on a journey to the very beginning of everything. Our story begins not in a high-tech lab, but at a giant horn-shaped antenna in Homedale, New Jersey, built by Bell Laboratories. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were using this sensitive instrument for routine observations. But they were plagued by a persistent, maddening problem, a constant, faint hiss of static that came from every direction in the sky. It was their day and night through every season. They checked and rechecked their equipment, even famously evicting a pair of pigeons and cleaning out what they called white dielectric material from the antenna, convinced it was the source of the interference. But no matter what they did, the inexplicable noise remained. This frustrating, seemingly mundane technical glitch would turn out to be one of the most profound scientific discoveries of the 20th century. What they were hearing was the faint, dying whisper of the universe's birth, the cosmic microwave background radiation. This omnipresent signal is the cooled-down remnant of the universe's fiery beginning. Imagine the Big Bang not as an explosion in space, but as the rapid expansion of space itself, filled with unimaginably hot, dense energy. For the first several 100,000 years, the universe was a searing, opaque fog of plasma, so thick that light particles, photons, couldn't travel any distance without immediately colliding with and being absorbed by free electrons. It was a brilliant but blinding cosmic soup. Then, as the universe expanded and cooled to a temperature of around 3000 Kelvin, something monumental happened. Protons and electrons finally combined to form the first neutral hydrogen atoms in an event cosmologists call recombination. Suddenly, the fog lifted. For the first time, photons could travel freely across the cosmos. That first flash of liberated light is what we detect today as the CMB. After traveling for over 13 billion years, the expansion of the universe has stretched those initial, high-energy photons into the microwave part of the electromagnetic spectrum. They have cooled to a mere 2.7 degrees above absolute zero, which is minus 270.45 degrees Celsius. This makes it one of the coldest things in the natural universe. Its temperature is astonishingly uniform, varying by only tiny, almost imperceptible fractions of a degree across the entire sky. This incredible uniformity was actually a major puzzle for cosmologists. How could regions of the universe on opposite sides of the sky, which could never have been in contact with each other, have reached the exact same temperature? This very question is what led theorists to develop the groundbreaking idea of cosmic inflation, a concept we will explore in detail very soon. the CMB is far more than just a relic. It is our most powerful window into the infant universe. By studying the minute fluctuations in its temperature, those tiny hot and cold spots that map onto the sky, scientists can read the blueprint of the cosmos. Those faint ripples are the seeds of all future structure. They represent slight variations in density, the gravitational anchors around which everything, every galaxy, every star, every planet would eventually form. Without those tiny imperfections drawn out by gravity over eons, the universe would be a vast, empty, and featureless void. The serendipitous discovery by Penzias and Wilson, for which they won the Nobel Prize, provided the first direct, tangible evidence for the Big Bang theory, cementing it as the cornerstone of modern cosmology and giving us our oldest family portrait of the universe. But if the faint whisper of the cosmic microwave background is the cooled-down remnant of the Big Bang, then the work of Edwin Hubble just a few decades earlier provided the first powerful clue that such an event must have occurred. While Penzias and Wilson were listening to the universe's birth cry, Hubble was watching the aftermath of the explosion itself, playing out in slow motion across the cosmos. In the 1920s, the prevailing view of the universe was that it was static and eternal, a vast, unchanging island of stars. But Hubble, working with the most powerful telescope of the age at Mount Wilson Observatory, was about to shatter that illusion forever. His revolutionary discovery began with the work of other astronomers, particularly Vesto Slipher, who had observed that the light from most galaxies was shifted toward the red end of the spectrum. This redshift is a phenomenon similar to the Doppler effect, which causes the siren of an ambulance to sound lower in pitch as it moves away from you. In space, this shift in light tells us a galaxy is moving away from us. Hubble took this concept of redshift and combined it with another crucial piece of the puzzle: distance. At the time, measuring the distance to far-off galaxies was incredibly difficult. Hubble's breakthrough came by identifying a special kind of star in these distant nebulae called a Cepheid variable. These stars pulsate with a regular rhythm, and the period of their pulsation is directly related to their true brightness. By comparing how bright the star appeared from Earth to how bright he knew it actually was, Hubble could calculate its distance with remarkable accuracy. It was like having a standard candle scattered throughout the universe. What he found when he plotted the distances of these galaxies against their velocities was nothing short of earth-shattering. The data revealed a stunningly simple yet profound linear relationship. The farther away a galaxy was, the faster it was receding from us. This is Hubble's law. It wasn't just that everything was moving away, it was that the speed of recession was directly proportional to the distance. This wasn't a random scattering of galaxies fleeing in all directions. This was the signature of a universe that is uniformly expanding. Think of the universe as a loaf of raisin bread rising in the oven. As the dough expands, every raisin moves away from every other raisin. A raisin that was originally twice as far away from you as another will end up moving away twice as fast. From the perspective of any single raisin, all the others appear to be fleeing, with the most distant ones moving the fastest. We are not at the center of this exodus. Any observer in any galaxy would see the exact same thing. This single observation completely rewrote our cosmic story. An expanding universe implies that if you could rewind the tape of time, all of that matter and energy must have been compressed together in the distant past. The entire observable universe, every galaxy, star, and planet was once contained in an incredibly hot, dense state. Hubble's law didn't just suggest a beginning, it demanded one. It provided the first direct observational evidence that the universe had a starting point, a moment of creation. This was the critical foundation upon which the entire Big Bang theory was built. While the cosmic microwave background would later provide the smoking gun, Hubble's discovery of the expanding universe was the compelling testimony that first pointed investigators toward the scene of the crime. His work transformed our cosmos from a static, eternal stage into a dynamic, evolving entity with a history and, ultimately, an origin story. Hubble's discovery of an expanding universe gave us the timeline, and the cosmic microwave background provided the baby picture, but a third pillar of evidence lies in the very chemistry of the cosmos itself. To find it, we have to journey back to a time even before the universe became transparent, to the first 3 minutes after the Big Bang, when the entire universe acted as a colossal, albeit short-lived nuclear furnace. This brief, explosive period is known as primordial nucleosynthesis, and the elements forged during those initial moments became the building blocks for everything that followed. In the very first second, the universe was far too hot for any complex structures to exist. It was a dense, raging soup of fundamental particles, protons, neutrons, and electrons bouncing around at near light speed, with photons of light so energetic they would blast any budding atomic nuclei apart instantly. But as the universe expanded, it cooled at an incredible rate. By the time 1 second had passed, the temperature had dropped to about 10 billion Kelvin, cool enough for neutrons and protons to begin combining without being immediately torn apart. However, this process was a delicate race against time, because free neutrons are unstable and decay into protons with a half-life of just under 10 minutes. The window for building the first elements was incredibly small. The main actor in this cosmic drama was the deuteron, a nucleus made of 1 proton and 1 neutron, which is the heavy form of hydrogen. For the first couple of minutes, photons were still so energetic that they would immediately destroy any deuteron that managed to form. It was like trying to build a sandcastle in the middle of a hurricane. But right around the 3-minute mark, the temperature fell below 1 billion Kelvin, a critical threshold. Suddenly, the energy of the photons dropped below the binding energy of the deuteron. The hurricane subsided. For the first time, these proton-neutron pairs could stick together. This was the starting gun for a frantic burst of nuclear fusion. With deuterons now stable, a rapid chain reaction began. Deuterons collided with other protons and neutrons to form helium-3 and tritium, and these isotopes quickly combined to form the incredibly stable helium-4 nucleus, which contains 2 protons and 2 neutrons. This process swept up nearly all the free neutrons that existed in the universe. In just a few minutes, about 25% of the mass of the ordinary matter in the universe was fused into helium-4. Trace amounts of other light elements were also produced, like lithium-7 and a tiny bit of beryllium, but the party was over almost as soon as it began. The universe continued to expand and cool so rapidly that within about 20 minutes, the density and temperature fell too low for any further significant fusion to occur. The cosmic furnace shut down, leaving behind a universe composed of about 75% hydrogen and 25% helium by mass, a composition that remains essentially unchanged to this day. The most stunning part of this entire story is the prediction. In the 1940s, physicists like George Gamow, Ralph Alpher, and Robert Herman worked out the detailed nuclear physics of these first few minutes. Using the known laws of nuclear reactions and the conditions of the early universe, they calculated what the abundances of these light elements should be. Decades later, when astronomers began to carefully measure the chemical composition of the oldest, most pristine objects in the universe, such as ancient gas clouds in intergalactic space and population, 2 stars in the halos of galaxies that formed from unpolluted material, they found a near-perfect match. The observed cosmic abundances of hydrogen, helium, and lithium align spectacularly well with the predictions from Big Bang nucleosynthesis. This agreement is not a vague coincidence, it is a precise quantitative triumph. The predicted helium abundance is exquisitely sensitive to conditions in the early universe, like the density of ordinary matter and the number of types of neutrinos. The fact that the calculations and observations align so perfectly tells us that our understanding of nuclear physics and the first few minutes of the universe is fundamentally correct. No other theory can explain why the oldest stars and the most remote gas clouds all share this same primordial recipe. It is a relic of a time before any stars were born, a fossil record etched into the cosmos itself, providing a third, independent and powerful line of evidence that points directly back to a hot, dense beginning. This remarkable uniformity of the cosmic microwave background, this near-perfect sameness in every direction we look, might seem like a comforting sign of a balanced and orderly cosmos. But for cosmologists, it presented one of the most baffling puzzles in modern physics, a problem so profound it threatened to undermine the entire Big Bang model itself. This is known as the Horizon problem, and understanding it requires us to think carefully about the speed limits of the universe. The issue is one of cause and effect, or more precisely, the inability for an effect to have a cause. In our everyday world, if you want to even out the temperature in a room, say, to make a cup of coffee in one corner the same temperature as a glass of water in the opposite corner, you need to mix them. You need to stir the air, allowing the molecules to bump into each other, transferring energy and eventually reaching a state of equilibrium. They need to be in contact to communicate. The universe has a strict speed limit for this kind of communication, the speed of light. Nothing, not even information, can travel faster. Now, let's apply this to the infant universe. The cosmic microwave background radiation we see coming from the eastern horizon of the sky has been traveling toward us for nearly 13.8 billion years. The radiation we see from the western horizon has also been traveling for the same amount of time. But here's the catch: those two regions of space from which that light originated are now billions of light years apart from each other. If we rewind the clock all the way back to the time of recombination, when the CMB photons were first set free, those two regions were already separated by a vast distance. In fact, the distance between them was so enormous that even if a signal had started traveling at the speed of light at the very moment of the Big Bang, it would not have had enough time to journey from one of these regions to the other to exchange heat and synchronize their temperatures. They were causally disconnected. Each region existed beyond the other's cosmic horizon, forever isolated and unaware of the other's existence. Yet, when we look at the map of the cosmic microwave background, the temperature of these two regions and every other pair of opposing regions in the sky is identical to within 1 part in 100,000. How is this possible? How can two parts of the universe that could never have exchanged a single photon of information, that were never in contact, know to calibrate their thermostats to the exact same setting? The standard Big Bang model, without any additional mechanisms, offers no answer. It predicts a universe that should be a chaotic patchwork of wildly different temperatures, a cosmic quilt of hot and cold spots that never had a chance to smooth themselves out. The fact that it isn't suggests something crucial is missing from the story. This profound conundrum demanded a radical solution, and in the early 1980s, a young physicist named Alan Guth provided a breathtakingly elegant one. He proposed a brief, spectacularly violent event that occurred in the universe's first fleeting moments, far earlier than nucleosynthesis or recombination. He called this theory cosmic inflation. The idea is that right around 10 to the power of -36 seconds after the Big Bang, the universe was seized by a peculiar kind of energy field, often likened to a gravitational force in reverse. This energy caused the fabric of spacetime itself to expand or inflate at a rate that is almost impossible to comprehend. For a sliver of a second, the universe doubled in size and then doubled again and again, completing perhaps 100 such doublings in less than the blink of an eye. This period of exponential expansion is the key that unlocks the Horizon problem. Inflation proposes that the entire observable universe we see today, all billions of galaxies across billions of light years, was before inflation began a tiny subatomic speck of space. And crucially, this tiny region was small enough to be causally connected. Every part of it was in close contact with every other part, allowing energy to be exchanged and a uniform temperature to be established, just like coffee and water evening out in a small cup. Then inflation struck. That tiny, thermalized, self-connected speck of space was stretched by an enormous factor, perhaps by more than a factor of 10 to the power of 26, smoothing it out to incredible uniformity and blowing it up to a size far larger than our entire observable horizon. In this stunning picture, the regions of the CMB that appear causally disconnected today were all once nestled together in that primordial, pre-inflationary dot. They had all the time in the world to reach a consensus on temperature before inflation flung them apart. The horizon problem isn't just solved, it's utterly erased. The universe is uniform for the same reason. Two spots on an inflated balloon are both part of the same balloon. They were together before you started blowing it up. Inflation takes a problem of physics and transforms it into a problem of initial conditions, providing an elegant and powerful mechanism that explains the universe's large-scale smoothness. But the horizon problem wasn't the only cosmic conundrum that inflation was poised to solve. Another, equally profound mystery lies in the very shape of the universe, a geometric puzzle known as the flatness problem. To understand it, we need to think of the cosmos not just as a collection of galaxies, but as a fabric of space-time that can itself be curved. According to Einstein's theory of general relativity, the density of matter and energy in the universe determines its overall geometry. This leads to three possible shapes, each with dramatic consequences for the ultimate fate of everything. If the density of the universe is greater than a specific critical value, then space-time will be curved back on itself into a closed geometry like the surface of a sphere. In this scenario, the universe would eventually stop expanding and collapse back in on itself in a big crunch. On the other hand, if the density is less than this critical value, space-time would have an open, saddle-like shape, curving away from itself and expanding forever into a cold, dark, and empty future. But there is a precise knife-edge balance between these two extremes. If the density is exactly equal to the critical density, the geometry of the universe is flat, like a sheet of paper extending infinitely in all directions. In a flat universe, expansion continues forever, but it slows asymptotically, never quite stopping. Now, here's the puzzle. For the universe to have either a closed or open geometry today, its initial density at the time of the Big Bang would have had to be incredibly fine-tuned away from the critical value. However, for it to be flat, the initial conditions would have had to be fine-tuned to a level that is almost beyond comprehension. Let's put some numbers on this. If 1 second after the Big Bang, the density of the universe had differed from the critical density by even 1 part in a million billion, that tiny deviation would have been magnified by billions of years of expansion. By today, the universe would either be visibly, measurably closed and collapsing, or so vastly open and empty it would be unrecognizable. Yet, our most precise observations, particularly from satellites like WMAP and Planck that study the cosmic microwave background, tell us that the universe is flat to within a margin of error of just 0.25%. The density we measure is almost exactly the critical density. This presents an enormous fine-tuning problem. How did the universe get its balance so perfectly right? Without some physical mechanism to explain it, a flat universe seems to require impossibly precise initial conditions, as if someone dialed in the density of the cosmos to a value with unimaginable accuracy at the moment of creation. This is the flatness problem. It suggests that the universe we live in is special, and that feels deeply unsatisfying to physicists, who generally expect the laws of nature to produce outcomes that are robust and not dependent on seemingly magical starting points. This is where cosmic inflation performs its second spectacular act of cosmic magic. Remember that inflationary period of hyper-fast expansion. It doesn't just smooth out temperature differences, it also acts like a master cosmic iron, relentlessly flattening the geometry of spacetime. Think of it this way: no matter how wrinkled a bedsheet might be, if you stretch it enough in all directions, any small-scale wrinkles vanish and the sheet becomes flat and smooth on large scales. The curvature of any small region becomes negligible when you zoom out. Inflation does exactly this to the fabric of the universe. That brief period of exponential expansion stretched the observable universe by such an enormous factor that any initial curvature it might have had was stretched out to near perfect flatness. In this view, we don't need to explain why the universe was born with impossibly perfect fine-tuning. Instead, inflation takes a wide range of possible initial conditions, a universe that could have been slightly open, slightly closed, or nearly flat, and drives them all toward a state of flatness. It is a physical process that naturally produces the precise, flat universe we observe today, without any need for mystical fine-tuning at the beginning. The fact that we measure a flat geometry is no longer a puzzling coincidence. It is a direct prediction and a powerful piece of evidence that a period of inflation truly did occur, ironing out the wrinkles of spacetime in the universe's first fleeting moments. So inflation masterfully solved two of the Big Bang's greatest puzzles, creating a universe that is both incredibly smooth and geometrically flat. But this solution came with a breathtaking and deeply profound bonus, a mechanism for creating something from almost nothing. You see, if inflation had worked too perfectly, it would have left the universe utterly featureless, a vast, empty, and boring void. A perfectly smooth distribution of matter would have meant no clumps, no variations in density, and therefore no gravitational anchors to eventually form galaxies, stars, or us. For the universe to have any structure at all, it needed a blueprint, a set of tiny imperfections to get gravity started. Incredibly, inflation didn't just provide the blank canvas, it also provided the brushstrokes, and it did so by tapping into the most bizarre and fundamental aspect of reality, quantum mechanics. To understand how, we have to shrink our perspective down from the cosmic scale to the subatomic. In the quantum world, empty space is not truly empty. It is a seething, bubbling foam where particles and antiparticles constantly flicker in and out of existence. These are quantum fluctuations, a fundamental uncertainty baked into the fabric of reality itself, governed by Heisenberg's uncertainty principle. For a fleeting moment, energy can be borrowed to create a particle-antiparticle pair, which then almost immediately annihilate each other, paying the energy loaned back to the vacuum. This chaotic dance is happening everywhere all the time, even in what we perceive as a perfect vacuum. On the human scale, these fluctuations are utterly insignificant and invisible. But during the inflationary epoch, something miraculous happened to these tiny quantum jitters. Recall that inflationary expansion was not just fast, it was exponential, stretching a region of space smaller than a proton to a size larger than the entire observable universe in a fraction of a second. This hyper-stretching did something extraordinary to those minuscule quantum fluctuations in the inflationary field itself. Imagine dipping a tiny paintbrush into a pot of quantum paint and then stretching the canvas by a factor of trillions upon trillions. The infinitesimally tiny flecks of paint, those random quantum fluctuations, would be stretched out along with the fabric of spacetime, frozen into the large-scale structure of the universe. They were transformed from subatomic quirks into macroscopic ripples in the density of matter and energy. Regions that had a slightly positive fluctuation became ever so slightly denser, while regions with a negative fluctuation became ever so slightly less dense. Inflation took the microscopic randomness of the quantum world and imprinted it across the cosmos, creating a pattern of density variations that would serve as the cosmic seeds for all future structure. This process left its signature as faint temperature variations in the cosmic microwave background. Those tiny hot and cold spots we see in the CMB map are not random noise. They are a direct snapshot of these stretched quantum fluctuations from the end of inflation. The slightly hotter spots correspond to regions that were marginally denser, where the photons had to climb out of a slightly deeper gravitational well, losing a bit more energy in the process. The slightly colder spots correspond to the less dense regions. The pattern is not random. It has specific statistical properties that align perfectly with what physicists would predict from quantum fluctuations amplified by inflation. It is the universe's first photograph, and it is a picture of quantum mechanics written across the sky. But these seeds were just the beginning. For nearly 400,000 years after recombination, the universe continued to expand and cool, and those tiny density variations were still far too small to collapse under their own gravity. The universe entered a period known as the Cosmic Dark Ages. Then, as the first stars and galaxies began to ignite, a new chapter began, the era of structure formation driven by gravitational instability. Gravity is the great architect of the cosmos, and it works patiently over billions of years. A region of space that is even 1 part in 100,000 denser than its surroundings has a slightly stronger gravitational pull. Over time, it will attract more and more matter from the surrounding areas, growing steadily denser. Meanwhile, the less dense regions around it will be stripped of their matter, becoming even emptier. This snowball effect is how the faint fingerprints from inflation grew into the magnificent cosmic web we see today. The smallest overdensities collapsed first, forming the first stars and globular clusters. These then gathered into proto-galaxies, which merged through collisions to form the majestic spiral and elliptical galaxies we observe. Galaxies themselves were then drawn together by gravity along vast, invisible filaments of dark matter, forming massive clusters and superclusters that stretch across billions of light years, separated by enormous, empty cosmic voids. Every single galaxy, every cluster, every filament in this vast network can trace its origin back to those specific quantum fluctuations that were stretched to cosmic proportions during that incredible inflationary burst. The grand tapestry of the cosmos, with its brilliant galaxies and vast empty spaces, is therefore the direct result of quantum mechanics writ large, a connection between the very smallest and the very largest scales imaginable. If stretching quantum fluctuations into cosmic seeds was the monumental prediction of inflation, then finding direct physical evidence for that frantic expansion became the holy grail of modern cosmology. While the flatness and smoothness of the universe point strongly to inflation, the theory needed a more definitive signature to move from a compelling idea to an undeniable fact. For decades, scientists have been hunting for this final, crucial piece of evidence, the faint imprint of primordial gravitational waves, ripples in spacetime itself, generated during inflation's explosive beginning. The most ambitious and celebrated efforts to find this signal have taken place in one of the most extreme environments on Earth, the South Pole. Perched on the Antarctic plateau, the remote Amundsen-Scott South Pole Station offers a unique window to the cosmos. The air here is incredibly thin, dry, and stable for months on end during the polar winter, creating viewing conditions that are among the best on the planet for observing the subtle nuances of the cosmic microwave background. It is here that a collaboration of institutions deployed a series of incredibly sensitive telescopes known as BICEP, the background imaging of cosmic extragalactic polarization, and its more powerful successors, the Keck array. These are not traditional light-gathering telescopes with large mirrors. Instead, they are arrays of cryogenically cooled radio detectors designed to measure not just the temperature of the CMB, but a far more elusive property, its polarization. To understand what they were looking for, we need to picture the moment the CMB was born. When the universe became transparent during recombination, the last scattering of light off electrons imprinted a specific pattern of polarization onto the photons. Think of light as a wave vibrating in a particular direction. Polarization is the orientation of that vibration. The gentle squeezing and stretching of space by sound waves traveling through the primordial plasma created a dominant, curl-free pattern of polarization called E-mode. These were detected in 2002 and provided a fantastic confirmation of our standard cosmological model, but inflation predicts something far more profound. The violent, exponential expansion of spacetime would have been so explosive that it would have generated powerful gravitational waves, literally sending ripples through the fabric of reality. These ripples would have subtly twisted the polarization of the CMB light as it was being set free, creating a distinct, swirling, curl-like pattern known as B-modes. Finding this primordial B-mode signal would be a direct detection of gravitational waves from the universe's first instant, providing an unprecedented glimpse into the energy scale of inflation itself. The hunt for these B-modes is arguably one of the most difficult measurements ever attempted in science. The signal is incredibly faint, a potential distortion buried in data that is 1,000,000 times fainter than the CMB temperature variations themselves. The BICEP and Keck teams spent years meticulously mapping a patch of the southern sky, scanning it over and over to build up an exquisitely sensitive picture of the CMB's polarization. They had to contend with not just instrumental noise, but a formidable foreground contaminant, polarized dust from within our own Milky Way galaxy. Interstellar dust grains aligned by galactic magnetic fields can also emit polarized light that mimics the swirling B-mode pattern, creating a potential false signal that could easily fool an experiment. In March of 2014, the BICEP-2 team made a stunning announcement that sent shockwaves through the scientific community and made headlines around the world. They reported with high confidence that they had detected this long-sought primordial B-mode signal. The scientific world was electrified. It seemed like the final proof of inflation had been found. However, in the rigorous world of physics, extraordinary claims require extraordinary evidence and must survive intense scrutiny. Further joint analysis with data from the European Space Agency's Planck satellite, which had mapped the Milky Way's polarized dust in incredible detail, revealed a sobering truth. The signal observed by BICEP-2 was overwhelmingly, if not entirely, due to this confounding galactic dust. The primordial signal, if it was there at all, was much weaker than initially thought. This was not a failure, but a critical lesson in the painstaking process of scientific discovery. The BICEP and Keck collaborations regrouped, incorporating the Planck dust maps into their analysis and continuing to collect more data with even greater sensitivity. Their subsequent results have not yet made another headline-grabbing detection, but they have placed the most stringent upper limits on the strength of the inflationary gravitational wave signal to date. These null results are themselves profoundly informative. They tell us that the energy scale of inflation was likely lower than some of the most grandiose models had predicted. Inflation still stands as the best theory we have for the universe's beginning, but the specific details of how it happened are being refined by these incredibly precise measurements. The search continues with next-generation experiments, each one building on the technical and analytical prowess pioneered by the tenacious teams braving the Antarctic cold, inching us closer to hearing the echo of spacetime's first tremors. While the heroic efforts at the South Pole were pushing the limits of ground-based observation, a different kind of explorer was operating in the pristine silence of space, undertaking a mission that would transform our understanding of the early universe from a sketch into a high-definition masterpiece. The European Space Agency's Planck satellite, named after the pioneering German physicist Max Planck, was not just another telescope. It was a time machine designed to listen to the universe's first cry with a clarity never before imagined. Launched in 2009 alongside the Herschel Space Observatory, Planck's sole purpose was to map the cosmic microwave background with such exquisite sensitivity and resolution that it would become the gold standard for cosmology, the definitive reference against which all theories would be tested. Its design was a marvel of engineering, built to achieve an almost impossible level of precision. Planck observed the sky from the second Lagrange point, a gravitational balancing point about 1.5 million kilometers from Earth in the direction away from the Sun. This location provided a supremely stable thermal and radiation environment, far from the interfering warmth and light of our planet and its star. The heart of the mission was its two instruments, the low-frequency instrument and the high-frequency instrument, both chilled to temperatures within a fraction of a degree above absolute zero to detect the faint whisper of the CMB against the vastly brighter emissions from our own galaxy. For over 4 years, Planck scanned the entire sky not once, but multiple times, patiently collecting trillions of data points to build the cleanest, most detailed all-sky map of the CMB's temperature and polarization ever produced. The results, released in 2 separate data sets in 2013 and 2018, were nothing short of revolutionary. Planck's map measured the temperature variations in the CMB, those all-important primordial density fluctuations, with a resolution down to 5 arcminutes and a sensitivity of a few millionths of a degree. To put that in perspective, it's like measuring the size of a grain of sand on the Moon from Earth. This incredible precision allowed cosmologists to move beyond simply confirming the existence of these fluctuations. They could now study their specific statistical properties in minute detail, reading the fine print of the universe's birth certificate. The pattern of hot and cold spots follows a very specific distribution predicted by the inflationary paradigm, and Planck's measurements matched this prediction with stunning accuracy, leaving no doubt that a period of exponential expansion did indeed occur. But Planck's true power was not just in confirming existing theories. It was in its ability to rule out alternatives and constrain the vast landscape of inflationary models. Before Planck, theorists had proposed a wide zoo of possible models for how inflation might have worked, each involving different types of inflationary energy fields and predicting slightly different characteristics for the resulting fluctuations. Some models predicted stronger fluctuations on large scales, others on small scales. Some predicted a significant amount of primordial gravitational waves, while others predicted very few. Planck's data acted like a cosmic judge, delivering a verdict on these models with unwavering authority. Many popular and long-studied inflationary models were suddenly ruled out because their predictions no longer matched the exquisitely precise data. The universe, through Planck, was telling us exactly how its first moment unfolded, and it was a much more specific story than we had previously imagined. The mission provided the most precise measurements of the universe's core ingredients ever made. It determined the age of the universe to be 13.8 billion years with an uncertainty of less than 1%. It refined the Hubble constant, the rate of the universe's expansion, to a value of 67.4 kilometers per second per megaparsec. Most importantly, it confirmed with overwhelming certainty that the universe is geometrically flat, and it measured the exact amounts of ordinary matter, and dark energy with percent-level accuracy. We now know with confidence that ordinary atoms, the stuff of stars, planets, and people, make up just 4.9% of the cosmos. Cold dark matter comprises 26.8%, and the mysterious dark energy driving the accelerated expansion accounts for the remaining 68.3%. These numbers are not rough estimates, they are the foundational parameters of our universe, etched into the CMB and now read with definitive clarity by the Planck satellite. Its legacy is a cosmic reference book, a dataset so rich and precise that it will continue to guide and challenge theorists for decades to come, setting the stage for the next great discoveries about our origins. While inflation elegantly solved the Horizon and Flatness problems, it also answered a third, more obscure but equally critical puzzle that emerges when we push our theories of physics to their breaking point. This is known as the monopole problem, and it involves a hypothetical relic from the universe's earliest, most energetic moments, a particle so exotic that its predicted existence threatened to derail the entire Big Bang model. To understand why, we need to journey back to a time even before inflation, to an era of supreme unity when the fundamental forces of nature were indistinguishable from one another. The universe we inhabit today is governed by four distinct fundamental forces: gravity, electromagnetism, the strong nuclear force that binds atomic nuclei, and the weak nuclear force responsible for radioactive decay. But physicists have long suspected that this separation is merely a low-energy reality. As we mentally rewind the cosmic clock and the temperature and energy skyrocket, these forces should begin to merge or unify. Grand unified theories, or GUT, propose that at the staggering energy of around 10 to the power of 16 gigaelectronvolts, which would have existed when the universe was just 10 to the power of negative 36 seconds old, the strong nuclear force and the electroweak force become one single unified force. This was the Jayuti era, a fleeting moment of perfect symmetry, and in this fiery cauldron of unification, theory predicts that a very peculiar kind of defect would have been mass-produced in abundance: magnetic monopoles. In our everyday experience, magnets always come with two poles, a north and a south. You can break a bar magnet in half, but you'll just end up with two smaller magnets, each with its own north and south pole. A magnetic monopole is a hypothetical particle that is just a north pole or just a south pole with no opposite counterpart. Such an entity is not forbidden by the laws of physics. In fact, Paul Dirac showed that their existence would neatly explain why electric charge is quantized, coming in discrete multiples of the electron's charge. Grand unified theories naturally predict that these monopoles would have been created copiously during the phase transition at the end of the GUT era, as the unified force broke apart into the separate forces we know today. Think of it like the formation of cracks in ice. When water freezes, its symmetrical liquid state gives way to a crystalline solid state. The transition isn't perfect. Defects and boundaries form between different crystal domains. In a similar way, as the universe cooled through the critical Jayuti energy, the symmetrical Higgs field that governed this unity would have settled into its new, lower energy state. But it wouldn't have settled the same way everywhere. Different regions of space would have chosen different orientations for this field, and where these cosmic domains met, topological defects would form. In 3 dimensions, the most stable of these defects is a point-like singularity, a magnetic monopole. These particles wouldn't be tiny. They would be incredibly heavy, monstrously dense objects with a mass 10 to the 16 times that of a proton, perhaps as heavy as a bacterium compressed into a subatomic particle. This is where the problem arises. The standard Big Bang model without inflation predicts that these monopoles would have been produced in overwhelming numbers, roughly 1 monopole for every proton in the universe. Given their immense mass, this density would have been catastrophic. The energy density of the universe would have been utterly dominated by these relic particles. They would have curbed the expansion of the universe long before galaxies could ever form, and their gravitational influence would be so profound that the universe would have recollapsed into a big crunch in a fraction of a second. Our universe, filled with galaxies, stars, and planets, simply could not exist if this prediction were true. And yet, despite decades of searching with incredibly sensitive experiments, not a single magnetic monopole has ever been conclusively observed. Their absence is a glaring contradiction between elegant theoretical prediction and observational reality. Once again, cosmic inflation provides the perfect and most elegant solution. The period of hyper-fast exponential expansion acts as the ultimate cosmic dilutant. Remember that inflation takes a tiny, subatomic patch of space and inflates it to a size larger than our entire observable universe. That original patch would have contained all the monopoles produced during the GUT phase transition, perhaps a very large number in that tiny volume. But then inflation stretches that volume by an absolutely unimaginable factor, perhaps 100 orders of magnitude. This dilutes the density of monopoles to effectively zero. It's like taking a single drop of ink and placing it in the middle of the Pacific Ocean. After stirring the entire ocean, the concentration of ink would be so infinitesimally small that you could never hope to find a single molecule of it. Inflation spreads the monopoles so thin that the average density in our observable universe becomes less than 1. They are still out there, but they are now so incredibly rare that the chance of one ever passing through our detectors is vanishingly small. The monopole problem isn't just solved, it's erased, transforming a catastrophic theoretical prediction into a harmless, undetectable footnote and allowing our universe of light and structure to exist. While inflation set the initial conditions and the cosmic microwave background gave us a baby picture, there is another incredible discovery that provides a completely different way to measure the expansion history of the universe, one that acts like a fossilized echo frozen in the large-scale structure of the cosmos. This phenomenon is known as Baryon acoustic oscillations, and to understand it, we need to go back to the era before the CMB was released, when the universe was still a searing, opaque plasma. During this time, the cosmos was not silent. It was filled with a roaring symphony of sound waves, and the remnants of those waves are still visible today, imprinted in the way galaxies are spaced across the universe. The story of these sound waves begins with a fundamental tug of war. In the hot, dense early universe, ordinary matter, protons and neutrons, which cosmologists call baryons, was coupled tightly with light or photons. This created a single fluid known as the photon-baryon fluid. This fluid was under immense pressure from the intense radiation, which wanted to push it outward and make it smooth. But it was also being pulled inward by the relentless force of gravity, which wanted to clump matter together. This competition set up a series of pressure waves that rippled through the primordial plasma, much like sound waves moving through air. These weren't subtle ripples, they were the dominant feature of the universe for its first several 100,000 years. A cosmic din of compression and rarefaction moving at a significant fraction of the speed of light. These sound waves had a very specific maximum distance they could travel. They began propagating from every slight overdensity, every one of those quantum seeds we discussed from the moment the universe began. But they could only travel until the universe cooled enough for recombination to occur. The moment electrons and protons combined to form neutral atoms, the photons decoupled and streamed freely across the universe, and the sound waves suddenly lost their pressure support. The waves froze in place, their progress halted instantly. This moment of freezing locked in a very specific distance that the waves had managed to travel, about 500,000 light-years from their point of origin. This distance became a fundamental, standard scale imprinted on the distribution of matter. After this freezing, gravity took over completely. The dark matter, which had been quietly collapsing under its own gravity without interacting with the radiation, formed the gravitational wells into which the ordinary matter would later fall. The baryonic matter, which had been jostled by the sound waves, was now distributed in a very specific pattern around those original seed points. There was a spherical shell of enhanced density at exactly that 500,000 light-year radius, marking the furthest reach of the pressure wave with a slight underdensity inside that shell. Think of it like a single note from a bell that rings out and then suddenly freezes, leaving a permanent, faint circular ripple in the air around it. Now, imagine that same process happening from every single point in the early universe where there was a slight density variation. The result is a universe filled with a three-dimensional web of these faint, overlapping spherical shells. Over billions of years, as the universe expanded and gravity pulled matter into the galaxies and clusters we see today, this pattern was preserved, albeit stretched by the overall expansion of space. That original standard ruler of 500,000 light-years has been stretched to a colossal scale of nearly 500 million light-years across the modern universe. This means that if we could map the positions of millions of galaxies with extreme precision, we should see a subtle statistical preference for galaxies to be separated by this specific distance. It is not that every pair of galaxies is exactly this far apart. Rather, if you take a census of all galaxy pairs, you will find a small but significant excess of pairs with a separation of around 500 million light-years compared to other distances. It is a whisper of correlation in the cosmic noise, a faint echo of that primordial sound. This is precisely what astronomers have done, and the results are a triumph of modern cosmology. Massive galaxy redshift surveys, like the Sloan Digital Sky Survey, have painstakingly mapped the three-dimensional locations of millions of galaxies across vast volumes of space. By applying powerful statistical tools to these immense maps, they have detected this very signal. The characteristic scale of the baryon acoustic oscillations has been measured with incredible precision, and it serves as one of the most powerful tools in the cosmologist's toolkit. Because we know the true physical size of this standard ruler from our understanding of sound waves in the early universe, a size we can calculate from the well-measured properties of the CMB, we can use it to measure cosmic distances. By observing how much this ruler appears to be stretched at different points in the universe's history, we can track the expansion rate of the universe with phenomenal accuracy. This makes baryon acoustic oscillations an independent and powerful probe for testing our models of dark energy and the geometry of the cosmos. Measurements from galaxy surveys have provided stunning confirmation of the accelerating expansion driven by dark energy, and they agree spectacularly well with the results from the cosmic microwave background and supernova studies. The fact that these completely independent methods, one using the oldest light in the universe and another using the distribution of galaxies billions of years later, both tell the same story about the composition and expansion history of the cosmos, is a breathtaking validation of our entire cosmological model. The frozen sound waves from the fiery dawn of time have given us a permanent yardstick, allowing us to measure the growth of the universe itself and confirming the mysterious dark energy that shapes our cosmic destiny. These incredibly precise maps of the cosmic microwave background have given us far more than just a pretty picture. They have allowed us to perform a kind of cosmic forensics, examining the statistical properties of those primordial fluctuations with a level of detail that would have been unimaginable just a few decades ago. When cosmologists analyze the pattern of hot and cold spots, they aren't just looking at their size and temperature, they are studying their distribution across different scales, asking a fundamental question: are the fluctuations on large scales of the sky statistically identical to those on small scales? The answer to this question is encoded in a single, crucial number called the spectral index, and its measured value provides one of the most powerful clues about the exact nature of the inflationary energy that birthed our universe. The concept of scale invariance is key here. A perfectly scale invariant spectrum of fluctuations would mean that the relative strength of the density variations is exactly the same, whether you are looking at a patch of sky the size of a continent or the size of a solar system. In such a case, the universe would have no preferred scale. It would look statistically identical at any magnification, much like a fractal pattern. This is precisely what the simplest models of inflation predict. The quantum fluctuations that get stretched across the cosmos should produce a spectrum that is nearly, but not quite, perfectly scale invariant. The reason for this slight deviation lies in the physics of the inflationary field itself. As inflation proceeds, the energy density of the field driving the expansion very slowly decreases. This gradual change means that the properties of the quantum fluctuations being stretched are not exactly identical from the very beginning of inflation to its very end. The fluctuations generated later are ever so slightly different from those generated earlier. This is where the spectral index, denoted as NS, comes in. It is a parameter that quantifies how the strength of the fluctuations depends on their scale. A value of exactly 1 would indicate perfect scale invariance. A value greater than 1 would mean that smaller scale fluctuations are stronger than larger scale ones, while a value less than 1 tells us that larger scale fluctuations are slightly stronger. The predictions from Planck and other experiments are incredibly precise. The measured spectral index is NS equals 0.965 with an uncertainty of less than 0.5%. This value is distinctly less than 1. This tiny deviation from perfection is not an error bar, it is a monumental discovery. It tells us that the primordial fluctuations are indeed not perfectly scale invariant. The universe does have a very subtle preference, with the larger scale fluctuations being marginally more prominent. This number, 0.965, is far from just a dry statistic. It is a rich source of information, a fingerprint that allows us to discriminate between the vast array of possible inflationary models that theorists have proposed over the years. The specific value of the spectral index is tied directly to the mathematical shape of the potential energy curve of the inflationary field. Essentially, how steep or shallow the hill was that this field was slowly rolling down during the exponential expansion. A value this close to 1 but definitively below it strongly supports the idea of slow roll inflation, where the field evolved gradually and gracefully. It rules out more dramatic and abrupt models, telling us that our universe's birth was likely a smooth, rather than a jerky, process. This precise measurement effectively acts as a cosmic report card on inflation's performance. It confirms the broad inflationary paradigm while simultaneously telling us that the simplest single-field models of inflation are the ones that best match the data. The spectral index is therefore a direct link, a bridge between the abstract quantum physics of the universe's first moment and the large-scale structure we observe billions of years later. It transforms inflation from a compelling idea into a specific, testable, and quantitatively verified theory of the very beginning, bringing us closer than ever to understanding the trigger for all of existence. For nearly 400,000 years after the universe became transparent, a profound darkness settled over the cosmos. This was the cosmic dark ages, a period when the brilliant afterglow of the Big Bang had faded to a cold microwave whisper, and not a single star or galaxy yet existed to pierce the overwhelming blackness. The universe was a vast, expanding sea of neutral hydrogen and helium gas, silent and opaque to visible light. But this tranquil, dark era was not destined to last. A dramatic transformation was brewing, one that would tear apart the very fabric of these primordial atoms and flood the universe with light for a second time. This monumental event is known as the epoch of reionization, and it marks the moment when the first brilliant structures ignited, ending the Dark Ages and setting the stage for the universe we see today. The smoking gun for this great re-illumination comes from two very different yet complementary lines of astronomical evidence. The first involves using the most distant and luminous objects in the universe as cosmic flashlights. Quasars are the intensely bright cores of active galaxies, powered by supermassive black holes greedily devouring matter. Their light is so powerful it can be seen from the very edge of the observable universe. As this brilliant light journeys for billions of years to reach our telescopes, it passes through immense clouds of the intergalactic medium. Neutral hydrogen gas is very efficient at absorbing light at a specific ultraviolet wavelength of 121.6 nanometers, known as the Lyman alpha line. When astronomers point their spectrometers at these far-off quasars, they don't see a pristine, unimpeded beam of light. Instead, they see a dramatic telltale signature, a complete absence of light at wavelengths shorter than that Lyman alpha line. This creates a sharp drop-off in the quasar's spectrum, known as the Lyman alpha forest, or more dramatically for the most distant quasars, the Lyman alpha trough. It's as if the quasar's light has passed through an incredibly thick fog of neutral hydrogen, which has absorbed all the light at that specific wavelength and shorter. The crucial discovery was that for quasars beyond a certain distance, and therefore from a specific time in the past, this trough is absolute. This tells us that at that early epoch, the vast spaces between galaxies were filled with a pervasive fog of neutral hydrogen blocking the light. However, when we look at the spectra of quasars that are closer to us, and therefore from a more recent time, that deep trough vanishes. In its place, we see a forest of many individual, smaller absorption lines. This indicates that the pervasive fog has been burned away. The neutral hydrogen has been blasted apart, its electrons ripped away from their protons in a process called ionization, turning it into a transparent, ionized plasma. The light from the quasars can now travel mostly freely, only being occasionally absorbed by the small, leftover pockets of neutral gas that still exist within galaxies. By carefully measuring the redshift of the most distant quasars that still show the complete trough, astronomers have pinpointed when this great clearing occurred. The epoch of reionization was largely complete by the time the universe was around 1 billion years old. The second line of evidence comes from our oldest picture of the universe, the cosmic microwave background. While the CMB photons were set free during recombination, their journey wasn't entirely over. As they traveled through the later universe during the reionization epoch, a fraction of them had another encounter. When a CMB photon encounters a free electron, it can scatter off it. This scattering leaves a subtle but detectable imprint on the polarization of the CMB light. The pattern created is the large-scale E-mode polarization that we discussed earlier. By measuring the strength of this polarization signal, missions like Planck have been able to calculate the total number of free electrons those photons encountered along their journey. This, in turn, tells us the total amount of ionization that occurred after recombination. The data from Planck reveals that about 6% of the CMB photons were rescattered during reionization. This percentage allows cosmologists to determine the optical depth of the universe to electron scattering, and from that, they can calculate that the process of reionization likely began around a redshift of 15, when the universe was roughly 270 million years old, and was mostly complete by a redshift of 6, or about 1 billion years after the Big Bang. This beautifully confirms the story told by the distant quasars, but what was powerful enough to rip apart atoms across the entire observable universe? The prime suspects are the first generations of stars and galaxies. Known as population Roman III stars, these first luminous objects were behemoths, thought to be hundreds of times more massive than our Sun. They would have burned ferociously hot and bright, flooding their surroundings with an intense torrent of ultraviolet photons, each one carrying enough energy to break apart a hydrogen atom. The first quasars, powered by early supermassive black holes, would have also contributed their tremendous energy to this great ionization effort. It was likely a complex process, starting with isolated bubbles of ionized gas forming around the first stars and galaxies. These bubbles grew and eventually overlapped like rising foam in a sink, until the entire universe was once again transparent to ultraviolet and visible light, ending the Dark Ages and illuminating the cosmos for good. This brings us to a truly pivotal discovery, one that reveals the hidden architecture of the cosmos and the invisible hand that guided the assembly of everything we see. For all the brilliance of the first stars and quasars that ended the Dark Ages, they did not form in a random, featureless void. They were drawn into being along a vast, invisible scaffolding, a cosmic web woven not from ordinary matter, but from the gravitational pull of the mysterious substance we call dark matter. The story of how this shadowy framework emerged from the quantum seeds of inflation and grew into the universe's grand design is a testament to the power of both supercomputer simulations and deep space observation. We must first remember the profound difference between dark matter and the ordinary atoms that make up our world. Dark matter does not interact with light or electromagnetic forces at all. It neither emits, absorbs, nor reflects any form of radiation. Its only known interaction is through gravity. This means that while the photon-baryon fluid in the early universe was a roiling, pressurized sea, sloshing with sound waves, the dark matter was an entirely different entity. It was a cold, collisionless gas, unaffected by the intense radiation pressure that kept ordinary matter so smoothly distributed. This quality gave dark matter a crucial head start in the race to form structure. While ordinary matter was being pushed around by photons, the dark matter could quietly begin to respond to the pull of gravity alone. Those infinitesimal density fluctuations imprinted by inflation were just as present in the dark matter as they were in everything else. But for dark matter, there was no countervailing pressure to resist their growth. From the very first moments, regions of space with a slight overdensity of dark matter exerted a slightly stronger gravitational pull. This attracted more dark matter from the surrounding areas, making those regions even denser, which in turn increased their gravitational pull in a powerful feedback loop known as gravitational instability. This process began incredibly early, even during the first few 100,000 years when the universe was still opaque. By the time of recombination, when the ordinary matter was finally released from the grip of radiation, the dark matter had already laid down an extensive, albeit faint, gravitational framework. The ordinary matter, the hydrogen and helium gas, simply flowed into the gravitational wells that the dark matter had already prepared. The most compelling evidence for this narrative comes from the marriage of two powerful tools: immense cosmological simulations and exquisitely detailed maps of the real universe. Scientists create these simulations by programming the known laws of physics and the initial conditions from the CMB into some of the world's most powerful supercomputers. They define a volume of space, fill it with virtual particles representing dark matter, and set the simulation running to see how gravity sculpts it over billions of years of cosmic evolution. The results are nothing short of breathtaking. These simulations consistently show the cold dark matter collapsing first into a complex web-like structure, a cosmic network of dense knots connected by long filaments with enormous, empty voids in between. This is the famous cosmic web, and it emerges naturally from the gravitational collapse of those initial quantum fluctuations. When astronomers then point their most powerful telescopes at the night sky to create three-dimensional maps of the real universe, such as those from the Sloan Digital Sky Survey, they find a distribution of galaxies that matches the simulations with stunning accuracy. Galaxies are not scattered randomly. They are precisely traced along the filaments of the web, clustering densely at the intersections where multiple filaments meet. This is the ultimate confirmation that visible galaxies are just the lit-up traces of a much larger, invisible underlying structure. They are like lights on a Christmas tree, outlining its shape but not constituting the tree itself. The tree, the true structure, is made of dark matter. Its gravitational pull guided the gas that formed the stars and galaxies, determining the large-scale architecture of the entire cosmos. This understanding solves a major puzzle from the early universe. The first stars and galaxies formed with surprising speed, cosmically speaking. If ordinary matter had to collapse under its own gravity alone, starting from such a smooth state after recombination, it would have taken far longer than a few 100 million years to form the massive structures we observe. Dark matter provided the necessary gravitational kickstart. Its scaffolding was already in place, offering deep potential wells into which the ordinary gas could rapidly fall, condense, and ignite the first brilliant beacons of light. Without this invisible foundation, the cosmic dark ages might have lasted far longer, and the universe as we know it might never have come to be. Dark matter is not just a mysterious component of the universe. It is the essential architect, the silent builder whose gravity drew the blueprints from the quantum haze and constructed the stage upon which the visible universe would eventually play out its glorious evolution. Yet for all its predictive power, the discovery of dark energy as the dominant force in our cosmos has simultaneously unveiled what many physicists consider to be the most severe and embarrassing problem in all of theoretical physics. A problem of numbers so vast it defies human comprehension. This is the cosmological constant problem, a yawning chasm between prediction and observation that represents a 1 with 120 zeros after its level of disconnect. To grasp the sheer scale of this fine-tuning mystery, we need to journey into the bizarre world of quantum mechanics and the very concept of empty space. According to quantum field theory, what we perceive as a perfect vacuum is not empty at all. It is a seething, bubbling foam of virtual particles. Particle-antiparticle pairs constantly flicker into and out of existence, borrowing energy from the vacuum for an infinitesimally short time before annihilating and paying the debt back. This frenetic activity is not just theoretical. We see its effects in measured phenomena like the Casimir effect and the Lamb shift. All of this activity imbues every single cubic centimeter of empty space with a certain energy density, a background hum of the universe known as vacuum energy. This energy, according to Einstein's theory of general relativity, should have a gravitational effect. In fact, it should produce a repulsive force, a cosmic anti-gravity, that is mathematically equivalent to the cosmological constant term Einstein originally inserted and later discarded in his equations. This is where the problem arises. When physicists attempt to calculate how much energy this quantum vacuum should contain, they do so by summing up all the contributions from every possible quantum field and every possible frequency, all the way up to the Planck scale, the highest energy scale where our known physics is thought to break down. The result of this calculation is a number so astronomically huge it is almost meaningless. The vacuum energy density should be around 10 to the power of 112 ergs per cubic centimeter. This energy would generate a repulsive force so powerful that it would have ripped the universe apart in a fraction of a second after the Big Bang. Space-time would have curled in on itself so violently that not even atoms could have formed. But when astronomers measure the actual strength of dark energy's repulsive force through the accelerating expansion of the universe, they get a value that is shockingly small. The observed vacuum energy density is about 10 to the power of -8 ergs per cubic centimeter. This is not a small difference. The predicted value is a 1 followed by 120 zeros larger than the observed value. To say the prediction is off by 120 orders of magnitude is an understatement of cosmic proportions. It is like using the most sophisticated theories of fluid dynamics to predict the height of a wave and calculating that it will be taller than the observable universe, only to go to the beach and measure a ripple 1 millimeter high. This isn't a minor miscalculation. It suggests a fundamental flaw in our understanding, or that some miraculous cancellation is happening with impossible precision. This is the essence of the fine-tuning problem. For our universe to be habitable, for galaxies to form and life to evolve, the positive energy from these quantum fluctuations and the negative energy from gravitational binding must cancel each other out to at least one part in a 1 with 120 zeros. It appears that the universe has been perfectly calibrated to allow for our existence, a notion that makes physicists deeply uncomfortable. A universe that requires such inexplicable fine-tuning seems to point toward either an incredible series of coincidences we don't understand or the need for a revolutionary new theory that seamlessly incorporates gravity and quantum mechanics. The cosmological constant problem is therefore a glaring signpost, indicating that our current models are incomplete and that a deeper truth about the nature of reality is waiting to be discovered. This incredible journey of light from the Big Bang to our telescopes is not a straight and undisturbed path. The cosmic microwave background photons have traveled for nearly 13.8 billion years, and along their immense journey, they have encountered everything the universe has to offer, from vast clusters of galaxies to enormous clouds of dark matter. And just like light passing through a lens, their path has been subtly bent and distorted by the gravitational pull of all this intervening matter. This phenomenon is known as gravitational lensing, and its delicate imprint on the CMB provides cosmologists with a powerful tool to literally map the distribution of all matter, both seen and unseen, across the vast expanse of cosmic history. Gravitational lensing is a dramatic confirmation of Einstein's theory of general relativity, which tells us that mass warps the fabric of space-time. Light, always following the straightest possible path through this curved geometry, appears to bend as it passes near a massive object. We see spectacular examples of this when telescopes observe massive galaxy clusters acting as cosmic magnifying glasses, distorting the images of even more distant galaxies behind them into long, faint arcs. But the effect on the CMB is far more subtle. Instead of creating obvious arcs, the gravitational influence of all the matter between us and the surface of last scattering creates a very slight, statistical smearing of the CMB's temperature and polarization patterns. It's as if we are looking at the universe's baby picture through a faintly warped piece of glass, a glass whose warps and imperfections are themselves a map of all the structure that has grown since the picture was taken. The key to unlocking this information lies in statistical analysis. The primordial fluctuations in the CMB are, for the most part, randomly distributed, a Gaussian random field in technical terms. Gravitational lensing doesn't create new hot and cold spots. Instead, it subtly rearranges the ones that are already there. It slightly correlates the temperature at one point with the polarization at another in a specific way that would not occur naturally. By developing incredibly sophisticated algorithms to analyze the exquisite data from the Planck satellite and ground-based telescopes like SPT and ACT, scientists can detect this faint statistical signature. They can essentially reverse engineer the lensing process to calculate exactly how the light was deflected along its entire journey. This allows them to reconstruct a map of the projected mass distribution between us and the edge of the observable universe. What makes this so powerful is that this lensing map is uniquely sensitive to all matter, regardless of its nature. It doesn't care if the matter is glowing stars, cold gas, or completely invisible dark matter. If it has mass, it warps space-time and it leaves its fingerprint on the path of the CMB photons. This provides a truly independent census of the total matter in the universe, and the results stunningly confirm what other lines of evidence have suggested. The lensing map shows that the large-scale structure of the cosmos is dominated by the gravitational influence of dark matter, its hidden scaffolding guiding the growth of everything we can see. Furthermore, by combining this lensing map with other observations, like the distribution of visible galaxies, cosmologists can perform a cosmic cross-check, testing our models of how gravity works on the largest scales and how structure evolves over time. This has become a crucial test for our standard cosmological model, and so far it has passed with flying colors, providing yet another independent confirmation of our strange and wonderful universe, where the invisible is made visible through the gentle bending of ancient light. Yet this elegant mechanism of eternal inflation, while solving problems within our own cosmic horizon, opens the door to a possibility so vast and strange it fundamentally redefines our place in reality. If inflation, once started, is truly eternal, generating endless pockets of stopped inflation, then our universe may not be the universe at all. Instead, it might be just one infinitesimal bubble in a frothing, infinite sea of space-time, part of a grander structure known as the multiverse. This isn't science fiction, but a natural, though speculative, consequence of the same physics that so elegantly explains the flatness and smoothness of our cosmic home. The journey to this staggering idea begins with the behavior of the inflationary field itself. Think of this field not as a simple on-off switch, but as a complex landscape of energy, like a mountain range with high peaks and deep valleys. The process of inflation occurs when the field is perched high on a slope, its immense potential energy driving the hyper-fast expansion. Eventually, in any given region, the field will roll down into a valley, its energy dissipating and converting into the hot particles of a standard Big Bang, ending inflation locally and creating what we would call a bubble universe. But due to the quantum fluctuations we discussed earlier, this process isn't uniform. In some regions, random quantum jitters can kick the inflationary field back up the slope or into a neighboring plateau where inflation can continue. Because the inflating space is expanding so much faster than these non-inflating bubbles are forming, the overall process never stops. Inflation is eternal into the future, continuously spawning new bubble universes within an ever-expanding inflationary background. Now consider the implications of this endless cosmic foam. Each of these bubble universes forms in a valley, but the landscape of possible valleys is not uniform. In the framework of string theory and other advanced concepts, the valley that a bubble rolls into determines the local laws of physics. This is because the specific low-energy state, the vacuum, defines the fundamental constants. One bubble might roll into a valley where the strength of the electromagnetic force is slightly stronger, making atoms impossible to form. Another might land in a valley where the cosmological constant is vast and positive, causing it to tear itself apart instantly, while yet another might have a negative constant, causing it to recollapse immediately. Our universe appears to have a very specific and seemingly fine-tuned set of constants that allow for galaxies, stars, planets, and life. In the multiverse scenario, this isn't a miracle, it is a selection effect. We naturally find ourselves in one of the rare bubbles where the physics permits our existence. We are not a privileged center of creation, but simply residents of a neighborhood that happens to be habitable. This idea transforms the cosmological constant problem from a paradox into a potential prediction. The vacuum energy we measure isn't fine-tuned, it's simply the value that happened in our bubble. In the incomprehensible vastness of the multiverse, every possible value of the cosmological constant and every possible set of physical laws is realized somewhere. The embarrassing one with 120 zeros discrepancy between prediction and observation might simply be because the theoretical calculation gives an average value across the entire multiverse, while our local measurement is just one data point from our particular bubble. While this doesn't provide a concrete physical mechanism, it offers a profound shift in perspective on why our universe is the way it is. Of course, the multiverse hypothesis is fiercely debated. A major criticism is that it seems to fall outside the traditional bounds of scientific inquiry. If these other universes are permanently disconnected from ours by unimaginable stretches of forever inflating space, with no possible exchange of information or energy, can we ever truly test their existence? Proponents argue that while we may never directly observe another bubble, the theory that predicts them inflation makes testable predictions within our own universe. The detailed pattern of the CMB fluctuations and the specific value of the spectral index are consistent with the type of inflation that would be eternal. Furthermore, if a collision between two bubbles were to occur, it could leave a potentially detectable, though highly speculative, imprint on the CMB, a circular pattern of abnormal temperature variations. No such definitive collision signature has been found, but the search continues. The multiverse remains one of the most thrilling and controversial frontiers of cosmology, a breathtaking glimpse into a reality of potentially infinite beginnings, where the laws of nature themselves are not immutable decrees but local bylaws, varying from one cosmic island to the next in an endless archipelago of existence. But to truly understand the significance of this hunt, we need to grasp what a perfect Gaussian distribution would mean. Imagine the universe's initial density fluctuations were like the static on an old television set, a completely random pattern where every point is independent of every other point, with no hidden correlations or patterns lurking within the noise. This is the signature of a simple, single-field inflationary model, where one quantum field slowly rolled down its potential energy hill, stretching its quantum jitters into the cosmic seeds we see. A perfectly Gaussian pattern would be the ultimate sign of simplicity, a cosmic fingerprint with no swirls or walls, just smooth randomness. For decades, this was the default expectation, the null hypothesis that cosmologists worked with. The hunt for deviations from this perfect randomness, features known as non-Gaussianities, is therefore a hunt for complexity in the infant universe. It's the difference between hearing a single, pure note from a tuning fork and listening to the rich, complex chord of a symphony orchestra. Finding even a hint of non-Gaussianity would be like discovering that the cosmic static has a faint, repeating melody woven into it, telling us that the physics of inflation was far more intricate than we ever imagined. It could indicate that multiple fields were interacting during that explosive period, or that the inflationary field had a more complicated potential energy landscape than a simple, smooth hill. Perhaps it interacted with other particles, or maybe the transition out of inflation was not a graceful roll but a more dramatic event. Each type of non-Gaussian signal acts as a unique diagnostic tool, pointing toward a specific class of advanced physics operating at energies 1 trillion times higher than anything we can probe in particle colliders on Earth. Missions like Planck have been meticulously searching for this signal by analyzing the statistics of the hot and cold spots in the CMB with incredible precision. They don't just look at the spots individually, they search for subtle correlations between them. For instance, they look at 3-point correlations, asking if certain configurations of hot and cold spots are more or less common than a purely random Gaussian field would predict. A detection would manifest as a specific telltale shape in the data, a statistical skew that reveals the underlying interactions of the inflationary field. So far, the results have been both profound and humbling. Planck and other experiments have found no significant evidence for primordial non-Gaussianity. The universe's baby picture appears to be stunningly, almost boringly, Gaussian. This null result is itself a monumental discovery. It places incredibly tight constraints on the possible physics of inflation, effectively ruling out a huge swath of more complex multi-field models. The data strongly favors the simplest inflationary scenarios, where a single field evolved smoothly and slowly. It tells us that while the mechanism of inflation was spectacularly powerful, it may have been driven by a surprisingly straightforward and elegant process. The search continues with ever more sensitive experiments, as even the tiniest deviation from perfect Gaussianity would revolutionize our understanding. For now, the profound simplicity of the universe's initial conditions stands as a silent testament to the elegant physics that may have sparked everything into existence. This brings us to one of the most critical and precise measurements in all of modern cosmology, an effort to pin down the exact nature of the mysterious dark energy that is accelerating the expansion of the universe. We know dark energy makes up about 68% of the cosmos, but what is it really? Is it a constant, unchanging energy inherent to the vacuum of space itself, as Einstein's cosmological constant suggests? Or is it something more dynamic, a force that could evolve over time, perhaps even changing its very character? The answer to this question is encoded in a single, crucial number known as the equation of state parameter, denoted by the letter W. This parameter is the key that unlocks the ultimate fate of everything. The equation of state describes the relationship between the pressure and density of a substance. For familiar components of the universe, we know what this looks like. For regular matter and dark matter, which have no significant pressure, the value of W is 0. For radiation like photons, which exert pressure, W is 1/3. For a cosmological constant, a constant energy density filling the vacuum of space, the pressure is negative, and specifically, W is exactly -1. This negative pressure is the source of the repulsive gravity that drives the acceleration. The critical question for cosmologists is, does the observed value of W match -1, or does it deviate from it? A value exactly equal to -1 points to a simple, static cosmological constant. A value slightly different from -1, however, would indicate that dark energy is something more complex and dynamic, often referred to as quintessence, an evolving energy field that could change in strength over the history of the universe. Determining this value with high precision is perhaps the greatest observational challenge in cosmology, and it requires a three-pronged attack using the universe itself as a laboratory. Each major probe, supernova, the cosmic microwave background, and large-scale structure, measures the effects of dark energy at a different epoch in cosmic history. By combining them, we can trace how the strength of dark energy's influence has changed over billions of years. The first and most direct evidence came from those distant supernovae. Type Ia supernovae serve as standard candles, allowing astronomers to measure the distance to galaxies billions of light-years away. By comparing this distance to the redshift of the galaxy, we can map out the expansion history of the universe. The stunning discovery in the late 1990s was that the expansion is accelerating, and the data immediately began to constrain the value of W, pointing toward something consistent with -1. But supernova alone aren't enough. This is where the other pillars of cosmology come in. The cosmic microwave background, particularly from the Planck satellite, provides a snapshot of the universe at age 380,000 years. The precise pattern of fluctuations in the CMB is exquisitely sensitive to the total density of matter and dark energy in the universe, but it doesn't directly tell us about the dark energy's equation of state. Its power comes from acting as the anchor point for the entire expansion history. It tells us how much the universe has expanded since that early time. When we combine this anchor with the supernova measurements that map the more recent expansion, we get a much tighter constraint on W. It's like knowing the starting point and the ending point of a race and using that to calculate the runner's acceleration throughout. The third powerful probe is the large-scale structure of the universe, revealed by galaxy redshift surveys and the Baryon acoustic oscillations we discussed earlier. The BO feature acts as a standard ruler etched into the distribution of galaxies. By measuring the apparent size of this ruler at different cosmic times, we can measure how the expansion rate has changed throughout the universe's history. The growth of this large-scale structure itself is also affected by dark energy. While gravity works to pull matter together to form galaxies and clusters, dark energy's repulsive effect works against this, suppressing the growth of structure as the acceleration takes hold. By measuring how clustered galaxies are at different redshifts, we get another independent handle on the properties of dark energy. The magnificent triumph of modern cosmology is that when we perform this joint analysis, combining the data from supernova, the CMB, and large-scale structure, all three independent lines of evidence converge on the same breathtakingly precise answer. The current best measurement of the dark energy equation of state parameter is W equals -0.998 plus or minus 0.018. This value is completely consistent with -1. Within the margins of our most advanced instruments, dark energy behaves exactly like Einstein's cosmological constant. It appears to be a constant energy density of the vacuum, unchanging over time. The implications for the ultimate fate of the universe are profound. A cosmological constant, unchanging and eternal, leads to a specific and frankly bleak destiny known as the heat death or the big freeze. In this scenario, the acceleration will continue unabated. Distant galaxies will continue to fade from view, their light redshifted beyond detectability. Eventually, our local group of galaxies will merge into one isolated supergalaxy, while the rest of the observable universe will disappear into darkness. Over trillions of years, stars will burn out and black holes will slowly evaporate via Hawking radiation. The universe will approach a state of maximum entropy, a vast, cold, and nearly empty void where the temperature uniformly approaches absolute zero and no complex processes can ever occur again. The fact that our measurements so strongly favor this simple cosmological constant suggests that this quiet, cold, and lonely end is the most likely destination for our cosmos, a final equilibrium written into the fundamental equations of physics. But our cosmic inventory wouldn't be complete without acknowledging some of the most elusive and fascinating particles to emerge from the Big Bang ghosts that permeate every inch of the universe, passing through you and everything around you at nearly the speed of light right now in astounding numbers. These are cosmic neutrinos, and while they are famously difficult to detect individually, their collective gravitational influence on the evolution of the cosmos has left an indelible mark that we can now read in the oldest light and the largest structures. Neutrinos are elementary particles similar to electrons, but with a crucial difference: they carry no electric charge. This means they are immune to the electromagnetic force, allowing them to pass through entire planets with almost no chance of interaction. They were first proposed by Wolfgang Pauli in 1930 to explain a seeming violation of energy conservation in radioactive beta decay, and he famously bet a case of champagne that they would never be detected. Thankfully for physics, he lost that bet. We now know that these particles are produced in abundance in nuclear reactions, from the core of our sun to the cataclysmic explosions of supernova. But the most numerous neutrinos in the universe are far older than any star. They are relics, frozen fossils from the first second after the Big Bang. In the unimaginable heat of the universe's infancy, neutrinos were constantly being created and destroyed, locked in a tight thermal dance with protons, neutrons, and electrons. But as the universe expanded and cooled, roughly 1 second after the Big Bang, it crossed a critical threshold. The energy of particles dropped too low for them to interact with neutrinos effectively. At this moment, the neutrinos decoupled from the rest of the primordial plasma. They suddenly stopped interacting and began streaming freely across the expanding universe, much like the photons of the CMB would do hundreds of thousands of years later. This created a cosmic neutrino background, a sea of these ancient particles that should, in theory, fill all of space. But unlike the CMB, which cooled to microwave wavelengths, these neutrinos have cooled so much that their incredibly low energy makes them effectively impossible to detect with current technology. We cannot point a telescope and see their afterglow, so how do we know they are there, and how do we study them? We don't catch them directly. Instead, we observe their ghostly gravitational footprint. Even though individual neutrinos are almost massless, their sheer abundance is staggering. Scientists estimate there are about 336 of these relic neutrinos in every cubic centimeter of the universe. That means there are billions of them passing through your thumbnail every second. While each one exerts a negligible gravitational pull, the combined gravitational effect of this vast sea is significant enough to have subtly influenced how the universe evolved. Their primary influence was on the process of structure formation, and it is here that we find their signature. After decoupling, these relic neutrinos were moving at a significant fraction of the speed of light. This made them hot, dark matter. Their high velocity meant they could easily stream out of regions of slight overdensity, washing out or smoothing over the very smallest density fluctuations that were the seeds of future galaxies. This suppression of small-scale clustering is a key prediction of cosmological models that include neutrinos. The effect is subtle, but it leaves a specific imprint on two things we can measure with exquisite precision: the cosmic microwave background and the large-scale distribution of galaxies. This is where missions like Planck become neutrino hunters. The precise pattern of hot and cold spots in the CMB is a sensitive probe of the universe's constituents at the time of recombination. The presence of neutrinos affects how those sound waves in the primordial plasma propagated, subtly altering the relative heights of the peaks in the CMB's power spectrum. By measuring these peaks with incredible accuracy, Planck and other experiments haven't just confirmed the existence of these relic neutrinos, they have actually been able to count them, confirming the predicted number of 3 neutrino species with overwhelming confidence. Furthermore, they have placed a tight upper limit on the total mass that all 3 types of neutrinos can collectively possess. The other key measurement comes from mapping the universe's 3-dimensional structure. Massive galaxy surveys like the Sloan Digital Sky Survey allow us to see the results of the structure formation process. By statistically analyzing the clustering of galaxies on different scales, astronomers can detect the specific suppressing effect that neutrino mass had on the formation of the smallest structures. The combined data from the CMB and large-scale structure now tell us that the sum of the masses of the 3 neutrino types must be less than about 0.12 electron volts. To put that in perspective, that's more than 1,000,000 times lighter than an electron. This might seem like a small detail, but its implications are profound. First, it provides direct cosmological evidence for physics beyond the standard model of particle physics. For a long time, neutrinos were thought to be completely massless, as the standard model initially assumed. The fact that they have any mass at all, however tiny, is a monumental discovery that forces us to revise our most fundamental theories of particle physics. Second, by measuring their mass from the cosmos, we are performing a type of particle physics experiment on an energy and scale that no terrestrial collider could ever hope to achieve. We are using the universe itself as a laboratory and the CMB and galaxies as our detectors to probe the properties of particles that are nearly impossible to catch. These faint relic ghosts from the first second of time are not just passive bystanders in cosmic history. They are active participants whose subtle touch helped to sculpt the cosmic web we call home. Yet for all the spectacular predictive success of Big Bang nucleosynthesis, there remains one stubborn, glaring anomaly in the cosmic recipe, a single ingredient that just doesn't add up. This is the lithium problem, and it stands as the most persistent, unsolved puzzle from the universe's first 3 minutes. While the predicted abundances of hydrogen, helium, and deuterium match the observed values with breathtaking precision, the amount of lithium-7 we actually find in the oldest stars is consistently and perplexingly off by a factor of about 3. It's a discrepancy that has resisted explanation for decades, suggesting that our understanding of those initial moments, however refined, might still be missing a crucial piece of physics. The problem is one of both shortage and surplus, depending on which isotope of lithium you examine. The primordial nucleosynthesis calculations predict the production of 2 lithium isotopes, lithium-7 and the much rarer lithium-6. The models tell us that for every 10 billion hydrogen atoms, there should be about 4 or 5 atoms of lithium-7. However, when astronomers look at the ancient, metal-poor stars in the halo of our galaxy stars that formed from nearly pristine material and thus preserve the primordial chemical composition, they consistently measure a lithium-7 abundance that is only about 1/3 of that predicted value. Conversely, for lithium-6, the standard model predicts a virtually negligible amount, so small it should be undetectable. Yet some observations have suggested a non-zero and surprisingly high level of lithium-6 in these same ancient stars, adding another layer of mystery to the problem. This isn't a case of sloppy measurements or flawed observations. The detection of lithium in the atmospheres of these ancient stars is a delicate but well-established astronomical technique. By analyzing the precise wavelengths of light absorbed by these stellar atmospheres, spectrographs can identify the unique fingerprint of lithium atoms. The stars used for these measurements are carefully selected to be old and cold, ensuring their surface lithium hasn't been depleted by internal nuclear burning or other processes. The fact that so many independent studies using different telescopes and methods converge on the same discrepant result is what makes the lithium problem so compelling and so frustrating for cosmologists. Solving this puzzle has proven to be a formidable challenge, and scientists have pursued a wide range of potential solutions. One line of inquiry questions whether our understanding of the nuclear physics itself is complete. The predicted abundances are based on precisely measured nuclear reaction rates, but perhaps there is an unknown or poorly measured reaction pathway that could destroy lithium-7 or produce lithium-6 in the early universe. Researchers have meticulously re-examined the cross-sections of every relevant nuclear reaction, from those involving deuterium and helium to more exotic possibilities, but so far, no adjustment within the known framework of nuclear physics has successfully resolved the discrepancy without throwing off the perfect agreement of the other elements. Another possibility is that the lithium observed in ancient stars is not actually the pristine primordial value. Perhaps these stars have mechanisms to destroy lithium in their atmospheres over their multi-billion-year lifetimes, or maybe they inherited their lithium from interstellar gas that had already been processed and altered by previous generations of stars, however early they formed. Yet, sophisticated models of stellar astrophysics have struggled to identify a plausible and universal destruction mechanism that would affect all observed stars in exactly the same way, consistently reducing lithium by the same factor across the board. The uniformity of the problem across many different stars actually argues for a primordial origin of the discrepancy, not a stellar one. The most exciting possibility is that the lithium problem is a direct hint of new physics beyond our standard models of cosmology and particle physics. Perhaps an unknown type of particle was present in the early universe, subtly altering the nuclear reaction network. Certain hypothetical particles, like some types of supersymmetric particles, could have affected the neutron-to-proton ratio at a key moment or provided alternate pathways for nuclear reactions, potentially depleting lithium-7 and enhancing lithium-6. Alternatively, the very constancy of nature's fundamental constants, like the fine structure constant, is occasionally questioned. Could they have been slightly different during nucleosynthesis, changing the reaction rates just enough to account for the lithium anomaly? While these ideas are speculative, the persistence of the problem keeps them alive, turning the humble lithium atom into a potential portal to a deeper understanding of the laws that govern our universe. It serves as a humble reminder that even our most successful cosmic theories may still be incomplete, and that the universe always has more secrets to reveal. What truly elevates cosmic inflation from a clever idea to a cornerstone of modern cosmology is its breathtaking predictive power. A good scientific theory doesn't just explain existing data, it makes bold, testable forecasts about what future observations should reveal. Inflation didn't merely offer a solution to the Horizon and Flatness problems after the fact. It laid out a specific blueprint for the universe that astronomers could go out and verify. This is where the theory moves from being mathematically elegant to empirically profound, and its predictions have been confirmed with stunning precision. The first and perhaps most dramatic prediction concerns the overall geometry of the cosmos. As we discussed, the flatness problem presented a universe that seemed impossibly fine-tuned. Inflation provided a physical mechanism to force the universe toward flatness, regardless of its initial curvature. This was an incredibly bold claim. It meant that if you could devise an experiment sensitive enough to measure the large-scale geometry of the universe, you would find that the angles of a giant cosmic triangle would add up to exactly 180 degrees, and parallel laser beams would never converge or diverge. This is precisely what subsequent missions, most notably the Wilkinson Microwave Anisotropy Probe and the Planck satellite, set out to test. By meticulously analyzing the pattern of hot and cold spots in the cosmic microwave background, these observatories measured the universe's geometry with unprecedented accuracy. The result was a definitive confirmation. The universe is flat to within a margin of error of just 0.25%. This wasn't just a lucky guess, it was a direct consequence of the exponential stretching during inflation, and its verification stands as one of the theory's greatest triumphs. The second major prediction was even more subtle and specific. Inflation posits that the seeds for all structure in the universe originated from quantum fluctuations that were stretched to cosmic size. The statistics of these quantum jitters have a very particular character. They should produce a spectrum of density fluctuations that is nearly, but not quite, scale invariant. This means the relative strength of the ripples should be almost identical across all scales, from the size of a galaxy to the size of the observable universe, but with a tiny, predictable deviation. This creates a specific fingerprint, a precise mathematical pattern, that should be imprinted on the cosmic microwave background. When the Planck mission finally mapped the CMB with exquisite detail, it measured this pattern, known as the spectral index, to be NS equals 0.965. This value is not 1, which would indicate perfect scale invariance, but is slightly less than 1, exactly as predicted by the simplest models of slow-roll inflation. The theory didn't just get the big picture right, it correctly forecast the minute details of the universe's first snapshot. This predictive success extends beyond these two headline findings. Inflation also naturally accounted for the absence of magnetic monopoles, a serious problem for the standard Big Bang model, by diluting them to effectively zero density. It predicted the existence of primordial gravitational waves, a signal that continues to be one of the most active areas of research in cosmology. Furthermore, the Gaussian nature of the fluctuations, the fact that the hot and cold spots are distributed in a random, statistical pattern without strange correlations, is another successful prediction. More complex theories often produce non-Gaussianities or specific patterns within the randomness, but the data from Planck strongly favors the simple, clean signature of single-field inflation. Each confirmed prediction strengthens the case, weaving a tight web of evidence that is incredibly difficult to explain with any alternative model. The ability of a single, elegant concept to make such a diverse array of precise forecasts that are then validated by observation is the hallmark of a truly powerful scientific theory, placing cosmic inflation among the most well-supported frameworks in all of physics. While our current maps of the cosmic microwave background are stunningly detailed, the next generation of observatories is poised to push our vision of the infant universe to unprecedented heights, transforming a clear photograph into an ultra-high-definition movie with sound. This new chapter in cosmic exploration is being written by a suite of ambitious international projects, each designed to answer the most profound questions left hanging by previous missions. Leading this charge are the Simons Observatory, currently under construction in Chile's Atacama Desert, the Japanese Lead Light Bird satellite mission scheduled for launch later this decade, and the colossal long-term endeavor known as CMB-S4. These aren't just incremental upgrades, they represent a quantum leap in sensitivity, resolution, and sheer technological ambition. The primary and most tantalizing goal for these next-generation observatories is the definitive hunt for the holy grail of cosmology, the primordial B-mode polarization signal caused by gravitational waves from inflation. Think of the CMB's polarization not just as a pattern, but as a rich audio signal. The E-modes we've already detected are like the melody, the clear, dominant notes of the cosmic symphony. But the B-modes are the baseline, the deep, fundamental rhythm that underpins the entire composition. Finding this faint, swirling patter would be like finally hearing the deep hum of the universe's birth cry. The challenge is that this signal is incredibly faint, potentially over 1 million times weaker than the temperature variations we can easily see. To detect it, these new experiments are deploying armies of detectors. The Simons Observatory, for example, will field over 60,000 superconducting detectors, all chilled to a fraction of a degree above absolute zero, working in concert to scan the sky with phenomenal speed and sensitivity. But the science goals extend far beyond just this one signature. These observatories will conduct a deep and systematic forensic investigation of the early universe. With their incredible resolution, they will create exquisitely detailed maps of the CMB's lensing effect, allowing us to construct a high-fidelity map of the distribution of all matter, dark and visible across cosmic time. This will let us measure the sum of neutrino masses with definitive precision, potentially finally pinning down the exact mass of these ghostly particles. They will also scour the CMB for any subtle signs of non-Gaussianity, those tiny, non-random correlations in the hot and cold spots that could reveal the fingerprints of multiple interacting fields during inflation or other exotic physics operating at energies far beyond the reach of any particle collider on Earth. Each project brings a unique strength to this global effort. The Simons Observatory, with its high-altitude desert base, acts as a powerful and agile pathfinder, demonstrating the revolutionary technologies at a scale never before attempted. The Lightbird satellite, orbiting at the second Lagrange point, has a singular, focused mission: to scan the entire sky with unparalleled precision to hunt for the large-scale patterns of primordial B-modes, free from the atmospheric interference that ground-based telescopes must contend with. And then there is CMB-S4, the ultimate culmination of this decades-long endeavor. Envisioned as a network of multiple telescopes in Chile and at the South Pole with over 500,000 detectors, CMB-S4 is designed to be the final word. It will deliver such an overwhelming volume of pristine data that it will either detect the inflationary gravitational wave signal beyond any doubt or rule out a huge swath of the remaining inflationary models, forcing a dramatic rethink of our cosmic origins. The data from these collaborations won't just test inflation, it will provide a stringent stress test for our entire standard model of cosmology. By delivering percent-level measurements of key parameters and searching for any discordant notes between the early universe and the late-time universe, they could uncover cracks in our understanding of dark energy or reveal entirely new fundamental particles. We are on the cusp of a new golden age of discovery, where the faint afterglow of the Big Bang will be read not as a static image, but as a dynamic storybook, revealing with breathtaking clarity the physical laws that govern the very first moment of time itself. While inflation has become the dominant paradigm for explaining the universe's initial conditions, its incredible success hasn't stopped physicists from exploring radically different ideas. The quest to understand the beginning of everything is too profound to rely on a single framework, no matter how compelling. This has led to the development of alternative theories that attempt to solve the same puzzles, the Horizon and Flatness problems, without invoking a period of exponential expansion. These competing visions offer fascinatingly different origin stories for our cosmos, and while they currently play second fiddle to inflation, they challenge our assumptions and ensure that cosmologists continue to rigorously test every possibility. One of the most captivating alternatives is the idea of a bouncing universe. This concept completely reimagines the Big Bang, suggesting it was not a true beginning from a singularity, but rather a dramatic transition from a previous phase of cosmic contraction. In this cyclic or bouncing model, our universe is part of an endless cycle of expansion and contraction. Imagine the cosmos as a giant cosmic lung, breathing in and out over trillions of years. A previous universe, perhaps very similar to our own, expands to a maximum size before the collective gravity of all its matter and dark energy halts the expansion and pulls it all back together in a big crunch. But instead of collapsing into an infinitely dense point of no return, something happens at the moment of maximum density. New physics, perhaps from quantum gravity or string theory, takes over and creates a powerful repulsive force, causing the universe to bounce and begin expanding again. The Big Bang, in this view, is simply our name for the most recent bounce. This scenario elegantly solves the horizon problem. Instead of requiring a tiny patch of the universe to be in causal contact before a sudden stretch, the bouncing model allows the entire universe an entire cycle, potentially hundreds of billions of years, to smooth itself out through natural thermodynamic processes. During the long contraction phase, matter and energy have ample time to interact and homogenize, reaching a uniform temperature. The bounce then transfers this smoothness to the new expanding phase. The flatness problem is also addressed. Each bounce naturally drives the geometry of the universe toward critical density, much like how repeatedly stretching a curved surface can make it appear flatter on large scales. Theories like loop quantum cosmology provide specific mathematical frameworks for such a bounce, replacing the classical singularity with a quantum bridge to a prior universe. Another intriguing contender comes from the world of string theory and is known as string gas cosmology. This approach posits that if we rewind time to the universe's very earliest moments, we cannot describe it as a point-like singularity governed by general relativity. Instead, we must consider it as a hot, dense gas of the fundamental strings that string theory proposes as the building blocks of all matter and energy. In this fiery, compact state, the strings would have vibrational energies near the Planck scale. A key prediction of string theory is the existence of extra, compactified dimensions of space. String gas cosmology suggests that the three spatial dimensions we observe are the only ones that manage to expand and become large, while the others remain tightly curled up. The theory proposes a natural mechanism for this. Only three dimensions are stable and capable of rapid expansion, while the others are dynamically prevented from growing. How does this solve the classic puzzles? The model suggests that the hot string gas was always in thermal equilibrium, meaning it had a uniform temperature. The strings, through their winding modes around the compact dimensions, could have stabilized the size of those dimensions and provided a natural explanation for the universe's observed flatness. Furthermore, string gas cosmology makes a unique prediction about the primordial density fluctuations. It suggests that the distribution of these fluctuations should not be perfectly Gaussian, but should contain a specific type of non-Gaussianity, a statistical signature that differs from the predictions of simple inflationary models. It also predicts a different spectrum of primordial gravitational waves, offering a clear observational target to distinguish it from inflation. So, with these elegant alternatives on the table, why does inflation remain the overwhelmingly favored model? The answer lies in the brutal, objective court of observational evidence. While bouncing cosmologies and string gas models offer conceptual solutions, they have struggled to produce the same level of precise, quantitative predictions that inflation has delivered. The measured pattern of fluctuations in the cosmic microwave background is exquisitely detailed. Its near-perfect scale invariance with a specific spectral index of NS approximately 0.965, its Gaussian statistics, and the observed coherence of fluctuations across vast scales all match the predictions of the simplest inflationary models with stunning accuracy. The alternatives have, so far, found it difficult to naturally reproduce this exact same set of observational facts without appearing contrived. Furthermore, inflation's predictions extend beyond the CMB. Its framework naturally incorporates and explains the vast cosmic web of galaxies we see today, seeding the structure that grew via gravitational instability. The alternatives are still playing catch-up in connecting their primordial mechanisms to the full, rich tapestry of the universe's large-scale structure that we have mapped in such detail. This isn't to say these ideas are invalidated. They remain vital areas of research precisely because they challenge the mainstream and force us to ask deeper questions. They are a necessary part of the scientific process, ensuring that inflation is not accepted on faith but is continually stress-tested. For now, inflation sits comfortably as the champion because it has successfully run the gauntlet of observational tests, but the search for an even better theory of the absolute beginning is far from over. But the breathtaking vision of an eternally inflating multiverse while solving one set of problems creates a profound new challenge that strikes at the very heart of scientific prediction. This is known as the measure problem, and it asks a deceptively simple question. In a reality where everything that can happen does happen an infinite number of times, how do we calculate the probability of anything? If the multiverse contains an infinite number of universes with every conceivable set of physical constants, then mathematically, any outcome you can imagine, from a universe made entirely of cheese to one where gravity is repulsive, is not just possible, it occurs in an infinite number of regions. An infinite number of universes will have laws of physics identical to ours, and an infinite number will have laws that are completely different. When you have two infinities, how do you determine which one is larger? How do you decide which outcome is more likely? This isn't just an abstract philosophical puzzle. It's a direct threat to the explanatory power of the entire multiverse concept. The original appeal of eternal inflation was that it could explain the apparent fine-tuning of our universe without invoking design or incredible coincidence. We live in a universe with a small cosmological constant and laws that permit life not because it's special, but because we couldn't exist anywhere else. This is the anthropic principle. But for this argument to hold any weight, we need to be able to show that life-friendly universes, while perhaps rare, are not impossibly rare. We need to be able to define what rare even means in an infinite landscape. If we cannot construct a sensible measure, a consistent mathematical rule for counting the different types of universes and defining probabilities, then the theory loses its ability to predict or explain why we observe what we do. It risks becoming untestable, a tale of infinite possibilities that can explain everything and therefore nothing. The core of the problem is that infinities break our everyday intuition about counting. Imagine an infinite hotel with an infinite number of rooms. You might ask, what fraction of the rooms have a view of the ocean? But if the hotel is built on an infinite coastline, there could be an infinite number of rooms with an ocean view and an infinite number without one. The fraction becomes undefined without a specific rule for how to count them. Do you count one room at a time? Do you count by floors? The answer you get depends entirely on your counting method. This is precisely the issue cosmologists face. The eternally inflating multiverse is that infinite hotel, and we need a non-arbitrary way to count the different types of rooms or pocket universes to determine whether our universe is a common or an exceptionally rare occurrence. Physicists have proposed various measures to solve this, each with its own strengths and bizarre consequences. One approach is to use a cosmic time coordinate, counting all the pocket universes that have nucleated by a certain time. Another is to use a volume-weighted measure, which counts the number of universes of a given type within a specified volume of the multiverse. The problem is that these different methods often yield wildly different answers. A volume-weighted measure might suggest that the vast majority of the multiverse's volume is dominated by regions where inflation has barely ended, making our old, large universe an extreme outlier. This could imply that we should actually be Boltzmann brains, freak, self-aware entities that randomly fluctuate into existence in a vast, empty space rather than evolved beings in a structured cosmos, which is a deeply unsatisfying and paradoxical conclusion. The search for a unique, well-motivated measure is one of the most active and thorny areas of modern cosmology. It forces us to confront deep questions about the nature of reality and the limits of scientific inquiry. Does a correct probability measure even exist, or is the concept of likelihood fundamentally meaningless in an eternal multiverse? finding a solution is crucial, not just for the sake of theoretical consistency, but for the future of cosmology itself. Without it, the majestic vision of the multiverse remains an intriguing but ultimately incomplete sketch, a story of cosmic genesis that brilliantly sets the stage but cannot yet tell us anything meaningful about the character of the players upon it. Yet for all its explanatory power, cosmic inflation feels less like a true beginning and more like a spectacular cosmic reset button. It tells us what happened immediately after the start, but it deliberately sidesteps the most profound question of all: what was the catalyst? What, if anything, preceded that first sliver of a second? To venture into that uncharted territory, we must push beyond the limits of Einstein's general relativity and into the enigmatic realm of quantum gravity, where the very concepts of space and time begin to break down and fray at the edges. This ultimate frontier is known as the Planck epoch, a period so early that the universe was a mere 10 to the power of -43 seconds old. At this scale, the universe was smaller than a single atom, and the energy density was so unimaginably high that the smooth, geometric fabric of spacetime described by Einstein dissolves into a seething, chaotic foam. Here, gravity is no longer a gentle curve in a continuum but a wildly fluctuating quantum field. General relativity, which governs the very large, and quantum mechanics, which governs the very small, meet at this point, and they clash violently. Neither theory can describe the conditions. We need a unified theory of quantum gravity to act as a translator between these two pillars of physics. Without it, our equations simply spit out infinities, the mathematical equivalent of a system crashing under an impossible load. Several ambitious theories have risen to this monumental challenge, each offering a radically different vision of the true beginning. One of the most compelling is loop quantum gravity. This framework imagines spacetime not as a smooth, continuous sheet, but as a fabric woven from tiny, one-dimensional loops. Think of it like a tapestry. From a distance it looks smooth and solid, but up close you see it's made of individual, discrete threads. In this view, there is a smallest possible unit of space, a quantum of volume, preventing matter from being crushed into an infinitely dense point. This leads to a breathtaking possibility. The Big Bang may not have been a birth from nothing, but a rebound from a previous universe. This is the concept of the Big Bounce. In loop quantum cosmology, as a previous universe collapses under its own gravity, it doesn't collapse into a singularity. Instead, the repulsive force generated by the quantum geometry of spacetime becomes so powerful that it halts the collapse and triggers a bounce, launching a new period of expansion, our Big Bang. In this scenario, time itself may extend backwards forever, an endless cycle of cosmic death and rebirth, with each new universe inheriting a quantum imprint from its predecessor. String theory, another leading contender, proposes a different kind of fundamental reality. It suggests the most basic building blocks of the universe are not point-like particles but incredibly tiny, vibrating strings. Their different vibrational frequencies determine whether they manifest as an electron, a quark, or a photon. For this mathematics to work, string theory requires extra dimensions of space, 6 or 7 of them, all curled up into a geometry too small for us to perceive. What does this mean for the beginning? Some string theory models suggest our universe could be a 3-dimensional brane, short for membrane, floating in a higher dimensional bulk. A cataclysmic collision between our brain and another one in this bulk could have injected an enormous amount of energy into our dimension, triggering the inflationary expansion we call the Big Bang. In this vision, the genesis of our cosmos was not an isolated event but a dramatic interaction in a much larger, hidden multidimensional reality. There are even more speculative ideas, like the concept of the universe arising from a quantum fluctuation in a pre-existing primordial vacuum. In this no-boundary proposal by James Hartle and Stephen Hawking, the universe would have no initial boundary in time, much like the North Pole has no boundary on Earth. Asking what came before the Big Bang becomes as meaningless as asking what is north of the North Pole. Time, as we understand it, would simply emerge alongside space and matter. These theories are not just mathematical exercises, they make different, testable predictions. Loop quantum gravity might leave a specific imprint on the polarization of the cosmic microwave background, while certain string theory models predict a specific spectrum of primordial gravitational waves. The ongoing hunt for these signals is in essence a search for fossils from the Planck epoch, a direct glimpse into the operating system of reality before our universe even booted up. While we may never have a complete and final answer, the quest itself forces us to refine our questions and expand our understanding of what it truly means for something to begin. So as we've journeyed from the faint hiss of the cosmic microwave background to the dizzying heights of the multiverse, what emerges is a story far more magnificent and bizarre than anyone could have imagined just a century ago. We've learned that our entire observable universe burst into existence from a subatomic speck, stretched to cosmic size in less than a blink of an eye during a period of hyper-fast inflation. This single idea doesn't just explain our origins, it solves profound puzzles telling us why the universe is so large, so flat, and so stunningly uniform in every direction we look. We've discovered that the grand tapestry of galaxies, with its brilliant clusters and vast empty voids, is nothing less than quantum mechanics written across the sky, the microscopic fingerprints of random fluctuations inflated to become the blueprint for everything. These revelations have completely rewritten our cosmic narrative. We now see the universe not as a static, eternal stage, but as a dynamic, evolving entity with a clear history, a story that begins with a hot, dense state and unfolds over billions of years, governed by a mysterious recipe of ordinary matter, and dark energy. We've peered back to the first 3 minutes to watch the primordial forge create the first atomic nuclei, and we've used the faint afterglow of creation itself to measure the universe's contents with percent-level precision. We've found that the very vacuum of space hums with a repulsive energy, accelerating the expansion of everything, and we've uncovered the invisible hand of dark matter, the silent architect that drew the blueprints for the cosmic web long before the first stars ever ignited. Yet for every question answered, a dozen more mysteries emerge. The cosmological constant problem remains a glaring 120 order of magnitude embarrassment, a silent scream for new physics. We still don't know what triggered inflation or what, if anything, came before it. The true nature of dark matter and dark energy continues to elude us, and the lithium problem whispers that our understanding of the first moments is still incomplete. We are left standing on the edge of a vast, potentially infinite multiverse, wondering if our universe is just one bubble in an endless, frothing sea of cosmic inflation. And so we are left with perhaps the most profound question of all. As we continue to build ever more sensitive telescopes and unleash the power of new technologies, what will the next great discovery be? Will we finally detect the primordial gravitational waves, the tremors from inflation's first moment? Will we uncover the particle nature of dark matter? Or will we find something entirely unexpected, a clue that forces us to once again rewrite the entire story of our cosmic home? The journey to understand our origins is far from over. What do you think is the universe's greatest remaining secret? Share your thoughts in the comments below, and be sure to subscribe as we continue to explore the deepest mysteries